Ever feel like your apps are speaking different languages? We dove deep into a technology that acts like a universal translator for the digital world Azure Service Bus.
Yeah, today's deep dive is all about Azure Service Bus. We've gone through a ton of research, really, to pay out the crucial bits for you.
Exactly. And just, in simple terms, what's the core idea here?
Think of it like a super reliable post office, but for your software applications, it's fully managed by Azure.
A post office.
Yeah.
Okay, so it helps them send and receive messages.
Precisely. Even if, like, one app is offline when the other sends something, Service Bus holds on to it.
Right. We've sifted through extensive research, like you said, to bring everyone the core insights.
Uh-huh. And our goal today is basically to unpack what Azure Service Bus is, why it actually matters for building, solid applications, and how understanding it helps you grasp the backbone of many modern systems.
And hopefully without getting totally bogged down in, like, super technical jargon.
We'll try our best. The aim is clarity.
Okay, let's unpack this because,
Yeah.
when you hear message broker, it can sound a bit intimidating.
It can, yeah.
But stick with us. We're going to explore some key ideas, how it helps different parts of your system work independently. That's decoupling, right?
Right, decoupling. Very important.
How it manages busy periods load balancing,
Right.
and how it lets things communicate without needing everything to happen, like right now, asynchronous communication.
And we'll definitely get into the two main ways Service Bus handles messages. Queues, which are more like point-to-point direct messages.
Learn ones.
Yeah, one-to-one. And then topics and subscriptions, which are more like broadcasting. Think publish, subscribe. One message goes out. Many can potentially receive it.
Okay, so fundamentally, what's Service Bus actually providing? What's the service?
So at its core, Azure Service Bus is an asynchronous messaging platform as a service, HaaS.
Pass.
And a huge thing here is the reduced management hassle. You, as the developer or user, you don't need to stress about the underlying servers, patching them, backing them up, none of that. Azure handles it all.
Nice. So less time wrestling with infrastructure, more time actually building things.
Exactly. That's the promise of PaaS, really.
Wow.
Now, to keep everything organized, your queues, your topics, all that stuff, you use something called namespaces.
Namespaces. Okay, like organizational units.
Think of them like that, yeah. Logical groupings for your messaging resources, kind of analogous to servers maybe, but it's all serverless from your perspective. Highly scalable.
Like cloud folders for messaging bits. Got it.
That's a good way to put it. And inside these namespaces live the actual messaging components, what Service Bus calls entities.
Entities. That's the queues and topics.
Queues, topics, and also the subscriptions that hang off the topics. Those are the building block.
So that's where the messages actually live and get processed.
Correct. And the messages themselves, well, that's the data you're sending. But a key thing to understand is a message isn't just the payload, the actual content. It also carries metadata. Think of it like the envelope and the address label. There's broker-defined stuff the system uses for routing and processing, and you can add your own user-defined properties.
Okay, so you can tag messages with extra info for filtering or specific handling.
Exactly. It separates the content from the how and why, the context and metadata.
Okay, makes sense. So we've got a basic picture, but why should someone building or managing apps really care about Service Bus? What are the big wins?
Well, we touched on it, but decoupling is probably one of the biggest. It massively boosts reliability and scalability.
How so?
Because the applications sending messages and the ones receiving them don't need to be online at the same exact time. They don't even need to know the other one exists, really.
Right. So if my, say, order processing service goes down for maintenance, my website can still take orders.
Precisely. The website just drops the order message into a queue, and the processing service picks it up when it comes back online. No lost orders, no website errors telling the customer to try again later.
That seems huge, especially for complex systems.
It is. Think about upgrading one piece of a machine without stopping the whole factory line. That's the kind of resilience it offers. It's particularly crucial in microservices architectures where you have lots of small independent services talking to each other.
Keeps things stable, yeah. What else? You mentioned load balancing.
Yes, load balancing. This is mainly with queues. A queue can distribute incoming messages across multiple consumers, multiple worker instances that are processing those messages.
So if I suddenly get a flood of traffic.
Exactly. You can just spin up more worker instances to pull messages off the queue. It prevents any single worker from getting overloaded and keeps things moving smoothly. Dynamically scalable.
Helps keep the application responsive under pressure.
Nice. And then there's the asynchronous communication aspect itself. sending a message even if the receiver is offline. The queue acts as that buffer, that shock absorber.
Like sending an email versus needing a live phone call?
Perfect analogy. It improves the responsiveness of the sender. It doesn't have to wait and handles bursts of traffic really well.
Okay, what about data consistency, like complex operations?
Good point. For scenarios needing high data integrity, Service Bus supports transactions. You can group several operations, like taking a message from one queue, processing it, and putting a related message onto another queue into a single atomic unit.
Atomic meaning, all or nothing.
Exactly. Either all the steps succeed, or if anything fails, the whole set of operations is rolled back. Think financial transactions. You can't have money disappear mid-transfer. It ensures consistency.
Critical for anything involving money or sensitive data flows.
Absolutely. Though it's worth noting, this transactional support isn't in the basic tier. You need standard or premium for that.
Okay, good caveat. And one more thing you mentioned, sessions for ordering.
Right, message sessions. These are really important when the sequence of messages matters. If you need strict first in, first out FIFO processing for a group of related messages again, think financial ledgers or maybe steps in a complex workflow sessions guarantee that order.
So messages sent within the same session are processed sequentially by the same receiver.
Correct. It pins a sequence of related messages to a single consumer until that sequence is complete. Sessions can also be used to build request-response patterns over messaging.
Okay, lots of powerful benefits there. Let's dig into those patterns more. First up, queues. Point to point. What's the essence?
Queues are fundamentally ordered containers for messages. A sender application puts a message onto the queue. A receiver application pulls a message off the queue. Simple concept.
Ordered, you said.
Yep. Messages are time-stamped when they arrive and generally kept in order. And like we just discussed, if you need strip FIFO for related messages, you use sessions on top of the queue.
Like queuing up at the checkout. First come, first served.
Pretty much. And crucially, once a message is accepted by the queue, it's stored durably.
Durably meaning it won't get lost if something crashes.
Exactly. It's typically stored with triple redundancy within the Azure data center. And you can even configure premium namespaces to span availability zones for even higher resilience against failures.
Okay. How do receivers actually get the messages? You said pull.
Yeah, the standard model is pull. The receiver asks the queue, "Got anything for me?" There's also a technique called long polling.
Long polling.
Where the receiver asks, but instead of getting an immediate nope, the request waits for a short period, maybe a few seconds, to see if a message arrives. It's much more efficient than the receiver constantly hammering the queue asking now, now, now.
Makes sense. Saves resources. So typical queue use cases.
Well, the big ones are temporal decoupling, separating sender and receiver in time, load leveling, smoothing out those peaks and troughs in workload. The competing consumer pattern is classic. Multiple identical workers processing tasks from a single queue as fast as they can.
Like a pool of workers grabbing jobs from a shared task list.
Exactly. And also just sending commands or specific tasks between different services in your application architecture.
Yeah, when a receiver gets a message, how does that work? Are there different ways?
Yes, two main receive modes. The simplest is receive and delete. The moment the receiver gets the message, it's removed from the queue.
Okay, but what if the receiver crashes after receiving but before processing?
Good question. That message is lost. That's why receive and delete provides at most once delivery. It's simple, but not always robust enough.
So what's the alternative?
The more common and robust mode is peak lock.
Peak lock.
Yeah. The receiver peeks at the message and Service Bus locks it, making it invisible to other receivers for a set duration. The receiver processes the message. If it succeeds, it explicitly tells Service Bus complete, and the message is deleted.
And if it fails? Or crashes?
If it fails, it can tell Service Bus abandon, which unlocks the message immediately, making it available again. Or, if the lock duration expires because the receiver crashed or took too long, the message automatically becomes visible again for another receiver, or the same one, to try processing. This gives you at least once delivery.
At least once, meaning it might get processed more than once if something goes wrong during the completion step.
Potentially, yes. Which is why applications using peak lock often need to be idempotent, meaning processing the same message multiple times has no additional side effects. Or you can enable Service Bus's built-in duplicate detection feature. If you combine peak lock with duplicate detection, you can get pretty close to effective exactly once processing guarantees.
Okay, that covers the one-to-one queue pattern pretty thoroughly. What about broadcasting? Sending one message to many receivers.
Topics and subscriptions, right?
Exactly. That's the publish-subscribe or pub-sub model. Contrast it with queues. Here, a publisher sends a message not to a specific queue, but to a topic.
A topic, like a broadcast channel. Precisely. And then multiple subscriptions can be attached to that topic. Each subscription essentially gets its own independent copy of every message sent to the topic.
Ah, so the topic is the bulletin board, and each subscription is like someone pinning their own copy of the flyer.
That's a great way to visualize it. Each subscription acts like its own virtual queue, receiving a filtered stream of messages from the topic.
Filtered, so subscriptions don't have to get every message from the topic.
Correct. That's a key feature. By default, a new subscription gets everything, but you can define rules and filters on each subscription.
Rules and filters, based on what?
Based on the message properties of the metadata we talked about earlier, both system properties and your custom ones. You can write conditions, often using SQL-like syntax, to say, I only want messages where property X equals value Y, or where property Z is greater than 100.
Wow, okay, so super flexible.
Very. You can even define actions as part of a rule to modify message properties before they land in the subscription's virtual queue. This allows for really sophisticated routing and categorization of messages.
So, use cases for pub-sub.
Oh, loads! Broadcasting updates, think product catalog changes, price updates, news alerts, sending event notifications across a system, order shipped, user registered, distributing the same piece of data to multiple downstream applications that might have different needs or processing logic. It's absolutely fundamental for building event-driven architectures. The publisher just fires off an event to the topic, and it doesn't need to know or care who's listening.
Totally decoupled. Makes sense. So how durable are these subscriptions? What if a subscriber is offline?
By default, subscriptions are durable. They'll hold on to messages for the subscriber until it comes online and processes them, just like a queue. You can set them to auto-delete after inactivity or expire messages after a certain time. And the premium tier also offers something called volatile subscriptions via JMS, which only exist while the client is actively connected.
Got it. So choosing between queues and topics. It really boils down to the communication pattern needed, one-to-one versus one-to-many.
That's the core difference, absolutely. If you're transferring specific business data from point A to point B, maybe an order from web front-end to back-end processing, a queue is often the natural fit.
Right, direct transfer.
If you need that decoupling for resilience or load balancing across multiple workers doing the same task, queue. But if you need to broadcast information, disseminate an event, or update multiple independent systems simultaneously, topic and subscriptions.
And what about those other features? Transactions, sessions.
If you need that all-or-nothing guarantee across multiple steps, transactions on queues or topic subscriptions require standard premium. If strict message ordering is critical or you're doing request reply, sessions, usually on queues but possible with subscriptions too, competing consumers for variable workloads. Queues. Need to prioritize some messages. Priority queues, a specialized queue setup. Buffering high-speed producers from slower consumers. Queue-based load leveling. It's all about matching the tool to the specific communication job.
Okay, let's peek under the hood a bit. You mentioned namespaces as containers. How does Azure actually run this stuff? Is it just a bunch of VMs I don't see?
Kinda, but much more sophisticated. That namespace you create isn't just a label. It represents a capacity allocation, a slice of compute and storage, within a large multi-tenant cluster of VMs managed by Azure.
A cluster.
Yeah, a highly available cluster that spans multiple physical locations within an Azure region, known as availability zones. So you get inherent high availability and scalability built in without you ever needing to manage those VMs, the patching, the OS, the failover logic. It's abstracted away.
So the namespace gives me my logical grouping, but Azure handles the physical resilience and scaling behind the scenes.
Precisely. Inside that namespace, you create your entities, queues, and topics. When a message hits a queue, it gets timestamped and put into durable storage, again, typically triple replicated.
And retrieval is usually pull-based.
Usually pull, yes. Though, as I mentioned briefly, for near real-time needs without constant polling, you can integrate with Azure Event Grid. Service Bus can push a notification to Event Grid when a message arrives, and Event Grid can then trigger, say, an Azure function or logic app.
Ah, like an event-driven trigger instead of polling. Cool. Now what happens if a message just can't be processed. It fails repeatedly.
That's where the dead letter queue, the DLQ, comes in. It's super important.
DLQ. Okay.
Every queue and every subscription automatically has its own associated DLQ. If a message exceeds its maximum delivery count, meaning receivers tried and failed to process it too many times, or if it expires due to its time to live, TTL, or if a subscription filter explicitly rejects it, the message isn't just deleted, it gets moved to the DLQ.
So it's like a holding pen for problematic messages.
Exactly. It prevents poison messages, messages that consistently fail processing, from blocking the queue indefinitely. You can then inspect the messages in the DLQ, figure out why they failed. Service Bus adds properties explaining the reason, fix the underlying issue, maybe bad data, maybe a bug in the receiver, and then potentially repair and resubmit the message or just log it for analysis.
So monitoring the DLQ is pretty critical for operations.
Absolutely essential. An overflowing DLQ is a sign something's wrong.
Got it. You also mentioned auto-forwarding.
Yeah, that's a neat feature for building workflows. You can configure a queue or a subscription to automatically forward any message it receives directly to another queue or topic within the same namespace.
Oh, so you can chain things together, like step 1 queue forwards to step 2 topic.
Exactly. It lets you build more complex routing patterns without needing an intermediary application component just to move messages around. Simplifies things.
What about sending messages for the future, like scheduling?
Yep. Scheduled delivery. You can submit a message now, but tell Service Bus not to make it available for processing until a specific time in the future. Useful for batch jobs that should run off hours, sending reminders, things like that.
And deferral? You mentioned that too.
Message deferral is slightly different. This is when a receiver gets a message using peak lock, but realizes it can't process it right now. Maybe it needs some other data that isn't available yet. Instead of abandoning the message, letting someone else try, or letting the lock expire, it can defer it.
Defer, meaning hide it temporarily.
Sort of. It takes the message out of the main queue flow but keeps it available. The receiver gets back a sequence number. Later, when it's ready, it can specifically ask Service Bus for that exact deferred message using its sequence number. It's for handling workflow dependencies.
Okay, complex state management. And finally, partitioning. You mentioned that for high throughput.
Right. Partitioned entity is available in Standard and Premium. Instead of your queue or topic living on just one internal message broker and store, it's spread across multiple partitions, each handled by a different broker-store combo.
Like sharding a database.
Similar concept, yeah. It dramatically increases the potential throughput because requests can be handled by multiple brokers in parallel. It also improves availability, as an issue with one partition doesn't necessarily affect the others. Standard tier partition entities can grow up to 80 gigabase.
Any downsides to partitioning?
The main one, especially in the standard tier, is that you lose the strict FIFO guarantee across partitions. Messages are still ordered within a partition, but not necessarily globally across the entire entity. Premium tier partitioning has some ways to mitigate this using session IDs or partition keys, but it adds complexity.
Trade-offs, as always. Okay, let's talk protocols. How do apps actually talk to Service Bus?
Several ways. The most recommended generally is AMQP 1.0, the Advanced Message Queuing Protocol.
Why AMQP?
It's very efficient. It uses persistent PCP connections, which reduces the overhead of setting up connections repeatedly. It supports features like batching messages together and prefetching, where the client library grabs a bunch of messages in advance really well. Plus, it's an open standard, which is great for interoperability and cross-platform development. Most of the official Azure SDKs use AMQP under the covers.
So default choice for performance. What else?
There's always HTTPS. Standard web traffic, secured by TLS, works everywhere, but generally has higher latency and overhead than AMQP because each operation might involve a new HTTP request response cycle.
Okay. And the third one, AMQP over WebSockets.
Right. This is basically AMQP traffic tunneled inside a standard WebSocket connection, usually over port 443, the same port HTTPS uses.
Why would you do that?
Firewalls. Sometimes corporate firewalls block the standard AMQP ports, 5671 and 5672, but almost always allow port 443 for web traffic. So AMQP over WebSockets lets you use the efficient AMQP protocol even in restricted network environments. There might be a tiny bit more initial connection latency compared to raw AMQP, but performance is generally very good after that.
Clever workaround for network restrictions.
Yeah.
Okay, super important topic, security. How do we lock this down? Authentication. Authorization.
Crucial. Service Bus has multiple layers. For auth, one option is shared access signatures, or SAS.
SAS tokens, I've seen those.
Yeah, they're basically tokens generated using cryptographic keys. You create SAS policies at the namespace level or on specific queue topics. Each policy grants certain rights: send, listen, manage. You generate a token based on a policy and key, and that token grants temporary access.
Seems flexible, but managing keys sounds tricky.
It can be. You need to secure the keys, rotate them regularly. It works, but Microsoft generally recommends using Microsoft Enter ID, what used to be Azure AD, for authentication whenever possible.
Enter ID, using OFTO tokens.
Exactly. It integrates with Azure's identity system, uses standard OAuth 2.0 flows. It's generally considered more secure, easier to manage identities and permissions, especially if your users and applications are already within your Azure tenant.
Okay, so Enter ID is preferred. What else? Managed identities.
Yes. Managed identities are fantastic for Azure resources talking to each other. If you have, say, an Azure function or an app service that needs to talk to Service Bus, you enable a managed identity for it. Azure handles the credential management securely behind the scenes. No connection strings or keys embedded in your code or config. Much safer.
No secrets in the code. That's a big win. Now, authorization controlling what someone can do once they're authenticated.
That's where role-based access control, RBAC, comes in. Service Bus has built-in Azure roles like Azure Service Bus Data Owner, Azure Service Bus Data Sender, and Azure Service Bus Data Receiver.
So you assign those roles to users, groups, or managed identities.
Precisely. You follow the principle of least privilege, only grant the permissions needed. You can assign these roles at the namespace level, or even better, scope them down to individual queues or topics for finer-grained control. This ties in nicely with Enter ID authentication.
Makes sense. Define policies at the right scope. What about the actual data? Encryption.
Right. Data at rest messages sitting in the queue or topic storage is always encrypted by default using Microsoft Managed Keys. Azure handles the key management automatically.
Always encrypted. Good. Any other options?
If you're using the premium tier and have stricter compliance needs, you can opt for Customer Managed Keys, CMK. You bring your own encryption key stored securely in Azure Key Vault, and Service Bus uses that key for encryption. You get more control, but also more responsibility for key management. CMK is a premium-only feature.
Okay. And data in transit between my app and Service Bus?
That's always secured using TLS transport layer security. Same stuff that secures HTTPS websites. It provides authentication, privacy, and integrity for the connection. Best practice is to configure your namespace to require a minimum TLS version, typically TLS 1.2 these days.
So secure connections are standard. What about network-level security? Can I stop random internet traffic hitting my Service Bus?
Yes, especially with the premium tier. It offers several network security features. First is virtual network VNet integration.
VNet integration, putting the Service Bus inside my private network.
Effectively, yes. You enable service endpoints for Service Bus on your VNet subnet. This routes traffic directly over the Azure backbone, keeping it off the public internet. It restricts access, so only resources within or peer to that VNet can reach the namespace.
Okay, better than public access. What's next level?
Private endpoints, also premium only. This gives your Service Bus namespace a private IP address directly within your VNet. All traffic to Service Bus then flows entirely over private connections. It's the most secure way, significantly reducing data exfiltration risks.
Private IP. So it's not even reachable publicly at all.
You can configure it that way, yes. You can explicitly disable public network access for the namespace, forcing all connections through private endpoints.
Wow. Okay. Any other network controls?
Premium also offers IP filtering. You can create rules to explicitly allow or deny connections based on specific public IPv4 addresses or ranges. So even if public access is enabled, you can restrict who can connect from the internet.
Lots of layers for security and premium. Good to know. Shifting gears to scale and reliability. You said Service Bus can handle millions of messages per second. How does it achieve that?
It's built for it. The premium tier, especially, is designed for high-throughput production workloads. It runs on dedicated resources, unlike Standard, which is multi-tenant, giving you predictable low latency and performance isolation.
Dedicated resources. That helps.
And it supports auto-scaling. You provision capacity in terms of messaging units, or MUs. If the CPU or memory usage on your allocated MUs gets high, you can configure it to automatically scale up adding more MUs to handle the load, and then scale back down when the load decreases.
Auto-scaling MUs, okay.
And as we discussed, partitioning is another key scaling technique available in Standard and Premium. Spreading the load across multiple brokers and storage units boosts throughput significantly.
Right, partitioning. What if even that's not enough? Extreme scale.
For truly massive scale, you might look at sharding your application. This usually means distributing your workload across multiple separate service bus namespaces, potentially even in different regions. It's more complex application-level design, but doable for extreme requirements.
Sharding across namespaces, okay.
Yeah.
How do we monitor this? How do I know if I need more MUs in Premium?
Azure Monitor provides detailed metrics for your namespace. You'd watch things like CPU usage, memory usage, incoming, outgoing message counts, request latency. A common rule of thumb for Premium is if your CPU usage consistently stays above, say, 70%, it might be time to add another MU.
Monitor the metrics. Got it. What about disaster recovery? Big outages.
Service Bus has several layers here, too. First, availability zones.
Basically, separate buildings in the same region.
Exactly. Both standard and premium tiers can be configured, often by default in regions that support them at no extra cost, to distribute their internal replicas across multiple AZs within a region. So if one data center has a major issue, the service can continue running from the other zones.
Protection against local failures. What about a whole region going down?
For that, you need cross-region strategies, primarily available in the premium tier. There's Geodisaster Recovery, GODR. This involves pairing your primary namespace with a secondary namespace in a different Azure region. Service Bus replicates the namespace metadata, queue names, topic names, authorization rules, etc., to the secondary region. If the primary region fails, you can manually initiate a failover, making the secondary namespace active. Note that this primarily recovers the structure, not necessarily the in-flight messages that hadn't been replicated yet.
Metadata replication. Okay. Is there something that replicates the actual messages too?
Yes, that's georeplication. It's a newer feature, also premium only, and was in public preview last I checked. It aims to replicate both the metadata and the message data across paired regions, allowing for failover and potentially failback with less data loss. It's more comprehensive, but also more complex.
Okay. Georeplication for full data DR.
Yeah.
Underlying all this is the basic message durability, right?
Absolutely. That triple redundant storage we mentioned earlier protects against common hardware or software failures within the data center itself. It's the foundation of message reliability.
Good. So last bit on this section, performance tuning. Any quick tips beyond using AMQP?
Sure. Definitely use AMQP. Leverage prefetching in the client libraries. Tell the library to grab, say, 10 or 20 messages at once instead of one at a time. Reduces network round trips.
Prefetch them. Okay.
Use asynchronous programming models in your code whenever possible. Don't block threads waiting for messages. Reuse your Service Bus client objects. Don't create new connections for every operation.
Reuse clients. Got it.
Batching. If you have multiple messages to send them as a batch. If you're receiving, try to receive a batch. Fewer network calls, less overhead.
Batch send, batch receive. Makes sense.
Be aware that features like sessions, complex filters, and transactions do add some overhead, so use them where needed, but maybe not everywhere if performance is absolutely critical.
Use advanced features judiciously.
Right. And watch message size. Standard tier limit is 256 KB per message. Premium goes up to 100 millibit if you use the AMQP protocol. If you have really huge messages, consider the claim check pattern.
Claim check pattern.
Where you store the large payloads somewhere else, like Azure Blob Storage, and just send a small message containing a reference or claim check to that payload via Service Bus. The receiver gets the small message, reads the reference, and then fetches the large payload directly from blob storage.
Clever way to handle large data blobs.
Oh.
Okay, let's talk money. Pricing, how does it work? Those
It's
tiers.
3 main tiers: basic, standard, premium.
Basic.
Cheapest, pay as you go for operations. Very limited features, queues only, no topics, no transactions, lower throughput, very few included connections. Good for dev test, maybe super simple, low volume production queuing, but really basic.
Standard, yeah.
Also pay as you go, runs on shared infrastructure. Much richer feature set, topics, transactions, sessions, deduplication, forwarding, scheduled messages, decent throughput. There's a small hourly base charge per Azure subscription that uses standard Service Bus, plus charges for operations and connections beyond a free monthly allowance, which is pretty generous, like millions of operations. Max entity size is typically 5 GB or 80 GB if partitioned. This is the workhorse for many general-purpose production apps.
Balance of features and costs. And premium.
This is different. It's consumption based on dedicated resources, priced per messaging unit, MU per hour. You choose how many MUs you need for your desired performance and scale them up or down or auto-scale. Includes all standard features plus benefits like resource isolation, predictable performance, GeoD replication, JMS 2.0 support, much larger message size, 100 milli on AMQP, VNet private endpoint support, IP filtering, CMK. Operations and connections are generally not charged separately. They're included within the MU capacity. Max entity size is 80 GB. Best for mission-critical, high-performance, high-security applications.
So premium is predictable performance, advanced features, pay for dedicated capacity. Standard is shared, pay per operation connection, good feature set. Basic is basic.
That's a good summary. And just quickly, things like hybrid connections and WCF relays, which are also part of the broader Service Bus product suite, have their own separate pricing models. We're focused on the core messaging here.
Got it. So what actually drives the cost up, especially in standard basic?
Primarily, the number of messaging operations sends, receives, completes, abandons, etc. In standard basic, messages larger than 64 KB count as multiple operations, which can add up.
Message size matters indirectly there.
Yep. Also, the number of concurrent brokered connections, especially in standard once you go over the free limit, which is about 1,000 concurrent connections. Basic has a very low connection limit. Premium doesn't charge per connection.
Okay. Operations and connections.
The chosen tier, obviously. And potentially data egress charges data transfer out of an Azure region usually costs money. Inbound and intra-region are typically free.
How can people manage these costs? Any tips?
First, pick the right tier. Don't pay for premium if standard meets your needs. Optimize message size, especially if you're on standard basic. Use batching extensively to reduce the number of operations. Reuse client connections factories, again, especially important in standard. Monitor your usage closely with Azure Cost Management Track Operations connections. Use long polling instead of rapid polling for receives. Try to stay within the free monthly grants on standard, if possible, for smaller workloads.
Good practical advice. Now, Azure has other messaging things, queue storage, event grid, event hubs. How does Service Bus fit in? When do you switch?
Great question. It causes confusion sometimes. Think of it like a spectrum.
Okay.
Azure Queue Storage, super simple, basic FIFO queuing, HTTPS-based, very high scale, low cost per operation, but small messages, 64 KB, no pub sub, no transactions, limited features. Good for massive scale, simple decoupling, task backlogs. Think AWS SQS equivalent.
Simple, high scale queuing. Got it.
Yeah.
Event grid.
Event grid is about eventing, reacting to things happening. Highly scalable, push-based pub sub. Designed for discrete event notifications. Blob created, resource group changed. Very low cost, serverless friendly. At least once delivery, but no guaranteed order. Ideal for reactive programming, wiring Azure services together. Think AWS Event Bridge equivalent.
Event-driven, reactive, unordered pub sub. Event hubs.
Event hubs is for massive scale data streaming and ingestion. Think telemetry, IoT data, application logs. Millions of events per second, low latency, provides ordered delivery within a partition. You typically read a stream of events rather than individual messages. At least once delivery. Think Kafkalite or AWS Kinesis.
Big data streaming, ordered within partitions. So Service Bus.
Service Bus is the enterprise message broker. Queues and topic subscriptions, rich features, transactions, sessions, ordering, duplicate detection, dead lettering, scheduling, filtering. Designed for reliable communication between applications, decoupling complex business processes, workflows that need guarantees, higher level abstraction than basic queues or event streams.
So, need transactions or strict FIFO across related messages? Service Bus. Need to react to Azure events, Event Grid. Need simple, massive scale queuing, queue storage. Need big data ingestion stream, event hubs.
That's a pretty good way to summarize the primary use cases, yeah.
How does this compare to, say, AWS? You mentioned SQS and Event Bridge.
Right. AWS tends to separate things more. SQS is just queues, like Azure Queue Storage. SNS is PubSub, like Event Grid plus Service Bus topics. Often you use SNS to publish, and an SQS queue subscribes to the SNS topic to get durable consumption.
So you combine SNS and SQS to get what Service Bus topic subscriptions do natively.
Often, yes. Azure Service Bus integrates queuing and PubSub more tightly within one service. Also, Service Bus Premium offers features like guaranteed performance, larger messages, VNet integration, etc. that go beyond the standard SQS-NS offerings. So Azure Service Bus is arguably more feature complete as a single broker service.
More integrated. What about Google Cloud PubSub?
Google Cloud PubSub is a very strong competitor. It's primarily a PubSub system, but can be used for queuing too. Highly scalable, real-time, Also supports event-driven patterns.
How does it differ from Service Bus?
Some nuances. Service Bus has built-in SQL-like filtering on subscriptions. GCP's filtering is maybe a bit different. Both have strong security. GCP is sometimes seen as simpler to set up initially and potentially scales to even higher volumes slightly more easily, though Service Bus Premium is incredibly scalable too. Service Bus can work over HTTPS easily, which helps with firewall sometimes. GCT PubSub historically had larger message size limits than Service as standard premium defaults, though Service Bus Premium's 100 millib AMQP limit is now very large.
So both powerful, maybe different strengths. Azure with broader built-in enterprise broker features, GCP perhaps with simplicity and extreme raw scale focus.
It's a fair characterization, yeah. The choice often depends on the specific features you need and the ecosystem you're already in.
Okay, enough comparisons. Where does this stuff actually get used? Real-world impact.
Industries. Oh, everywhere. E-commerce is huge. Order processing pipelines, payment notifications, inventory updates, syncing across systems.
Makes sense. Finance.
Absolutely. Secure, reliable communication for transactions, trade processing, regulatory reporting, ensuring data consistency is paramount there.
Others.
Telecommunications, provisioning services, sending billing notifications, handling network events, healthcare, securely exchanging patient information, following regulations like IP, appointment scheduling, critical alerts, manufacturing, optimizing production lines, tracking materials, reducing waste by reacting to sensor data, gaming, real-time leaderboards, broadcasting game events, player notifications.
Wow, really broad. Any specific examples?
Retailers like Save-A-Lot used Azure, including Service Bus, for modernizing their IT. Supply chains use it for order tracking, warehouse management workflows, marketing systems integrate with CRMs like Dynamics 365.
So it's the glue between different systems in many, many domains.
It often is, yeah. That reliable, asynchronous glue. It's used for triggering things like OCR processing in the cloud, automating infrastructure provisioning, building complex data pipelines, enabling communication in serverless apps like home automation.
Right, you mentioned functions and logic apps.
Exactly. Seamless integration there. You can even use it to implement the traditional enterprise service bus ESB pattern if you need that kind of centralized integration hub, though microservices often favor more decentralized approaches now. It can even bridge communication between different clouds sometimes.
Okay, it's clearly powerful and widely used. Let's wrap up with best practices. If someone is starting with Service Bus, what are the key things to get right?
Okay, let's break it down maybe into design, implementation, and management.
Sounds good. Design first.
Design. If you have multiple tenants or distinct applications, consider using separate namespaces for better isolation and performance tuning. For security, absolutely leverage VNet integration and private endpoints if you're on premium. Use IP filtering too if needed. Choose the right pattern upfront queue or topic subscription. Don't force one where the other fits better. Plan for scale. Think about partitioning early if you anticipate high volumes. Maybe budget for premium. For DR, plan for GeoDR or georeplication premium. Use sessions if you need ordering or request reply. Critically, design robust error handling. How will you deal with failures? Plan your DLQ strategy and retries.
Solid design points. Implementation. We're writing the code.
Implementation. Use AMQP for best performance. Handle exceptions properly. Service Bus SDKs throw specific exceptions. Catch them. Implement retry logic. The SDKs often have built-in retry policies too. Configure them wisely. Use prefetching. Code asynchronously. Handle message locks carefully in peak lock mode, complete, abandon, or defer appropriately, and respect the lock duration. Consider duplicate detection if exactly once is a requirement. Set sensible time to live, TTL, on messages so they don't hang around forever if unprocessed. Use the claim check pattern for huge messages. Secure connection strings. Use Key Vault. Use managed identities instead of keys connection streams where possible. Use the latest SDKs. They get performance improvements and bug fixes.
Good coding advice. Finally, management and monitoring, keeping it running smoothly.
Management monitoring. Monitor the dead letter queue. Seriously. Regularly. Set up Azure Monitor alerts for DLQ size, failed requests, server errors, resource health, namespace throttling, etc. Monitor performance metrics. Latency, throughput, CPU memory on premium MUs. Review and rotate your SAS keys periodically if you use them. Review RBAC permissions. Implement auto-scaling for MUs in premium if you have variable load. Be aware of quotas and limits for your tier. Tools like Azure Service Bus Explorer, a separate community tool but very useful, can help with direct inspection and management tasks.
Excellent checklist. Okay, Let's try to bring this all together then.
So Azure Service Bus, it's really a cornerstone service, isn't it? A powerful, versatile tool for building applications that are robust, scalable, and reliable, all thanks to its asynchronous messaging capabilities.
Yeah, and those core benefits we kept coming back to.
Decoupling gives you that flexibility and resilience. Load balancing helps handle peaks and keep things performing well. And guaranteed delivery, or at least well-defined delivery semantics like at least once, gives you peace of mind that messages aren't just lost in the ether.
It's really interesting to see how cloud messaging has evolved and where Service Bus fits. What do you think is next for it?
Good question. I'd expect, even tighter integration with serverless platforms like Azure Functions and Logic Apps, continued enhancements in security and compliance features to meet ever stricter requirements, probably more sophisticated monitoring, diagnostics, maybe even AI-driven insights into message flows and potential issues. It keeps evolving.
Definitely one to watch. So a final thought for our listeners. Maybe think about how these principles, asynchronous communication, decoupling message brokering, could actually change how your own systems talk to each other. What new things could you build if different parts didn't have to be so tightly linked?
That's a great takeaway. It really opens up possibilities. This has been a pretty deep dive into Azure Service Bus. If you listening have more questions or want to dig into a specific scenario, well, we're always up for another chat.